Alright guys, so this video will be about the nature of light and electromagnetic radiation. And the reason why we're going through this video is when we're talking about the structure of the atom and we're looking at ways that we can probe it, do experiments and find out how the electrons are arranged around this nucleus. Light and electromagnetic radiation in general plays a huge role. And the reason why is, if you remember from your earlier science classes, light is composed of two parts. You can see it from the name here, electromagnetic radiation. So it has two parts. It has an electrical component to it. It has a magnetic component to it, which means that it can interact with charged particles, and electrons are charged particles. So these electrons around the atom can interact with the electric field in the EM radiation. And by how it interacts, we can find out such things such as its energy. And how that energy flows and gets distributed. So it's a very kind of simple, very elegant, but also very useful probe of atomic structure. So thinking of light as a wave, so let's think of our typical wave. So our typical wave, it kind of looks like a sinusoid. Okay. It's probably not the best wave, but anyway, it has some parts to it. So we have this distance, which I mentioned in class, that's called the wavelength. So the wavelength, it's going to be measured in meters, okay, the SI unit of meters. And this is the distance between two successive, these are called crests, okay, so these top points are called crests, okay, so two successive crests. Down here, these are called troughs, by the way, okay, just for FYI purposes, these are called troughs. So it's the distance between two successive crests or two successive troughs, okay, but it kind of tells you how far apart they are. Now, another property of waves that will be important in our discussion is called frequency. So frequency. All right, so how do I explain this one? First of all, this is very often abbreviated with this kind of funny looking V thing. It's called nu. But frequency. So you imagine, these crests, and they're traveling towards maybe some point. And there's going to be a certain number of crests that pass through that point every single second. And the number of crests tells you how many oscillations there were, right? Because each crest corresponds to one oscillation up and down. And the number of oscillations, or the number of crests that pass through a certain point each second, is called the frequency. Okay, so this will have units of reciprocal seconds, and we very often call that hertz. Okay, so you can imagine that if we have a wave, and this wave has a set speed, and light does have a set speed. Light has the speed, we call it the c, 2.998, or if you want to round off, 3.0, 2.998 times 10 to the 8th meters per second. And this applies to all EM radiation, not just visible light, but IR, microwaves, ultraviolet, X-rays. They all have this the speed of light. Okay, this is the speed. Technically speaking, it's in the vacuum, but we'll go ahead and use that because it's very close to what it is in air as well. So all these waves have the speed. So you can imagine that if you shorten this wavelength, so if you make this wavelength here shorter, then you're going to have more crests hit that point every single second, and your frequency goes up. So these two, kind of play off of each other. And we have this equation that says that the speed of light, and this is, it can be generalized to any wave, but specifically the speed of light is going to be equal to the frequency of light times its wavelength. Okay, so that's a nice equation to know, where if we know what the frequency is, we'll know what the wavelength is, because we'll always know the speed of light, or microwaves or radio waves, whatever you got, we'll always have that speed right there. So that's an important equation, and you guys should write that down, because you might be required to do calculations with it. So we have this idea of light as a wave, and it works out very well. Light behaves as a wave. In a lot of ways, it can get you can have light interference. So if you have light passing through a small pinhole or a small opening, what you'll notice is that you'll see kind of like light and dark spots from the light waves interfering with each other. And waves are the only thing that does this. Okay, so like you'll notice that you'll have this interference pattern of light where you'll have dark and you'll have light light, bright, sorry, rays or lines. And so this is interference. There's also diffraction. So if you send it through a small slit, what will happen is light will spread out. It'll diffract like a wave as well. So light, for a long time we were thinking, okay, light's a wave. We got it. Light's a wave. We'll treat it as a wave. We'll do optics. We'll study optics with light as a wave. It works out. It worked out so well. It worked out well for quite a while until there were some experiments where it didn't work so well. So one of the experiments where it really was not working was in what's called the photoelectric effect. So what can happen is you'll have maybe like this piece of metal. Okay, so you'll have a piece of metal and light will come in, hit the piece of metal, and every now and then you'll have an electron get ejected. Okay, you can detect that electron. So very basic. This is what the photoelectric effect is. Now, here was the issue. Okay, according to classical physics, if light was just a wave, we can make this happen with any color of light that we had, because energy is related to how bright the light is. So if you're working electrons, you just made the light brighter. But what we found is that there was a frequency cutoff. So below certain frequencies, this wasn't happening. Below certain frequencies, the photoelectric, that's what P stands for, the photoelectric effect, yeah, I can write effect. All right, so the photoelectric effect does not occur. That is counter to classical physics. That was very confusing. Above a certain frequency, it would occur no matter how dim the light was, okay? And so someone had to explain this, and that someone who finally explained this was Einstein. And you can read in your book if you're interested in the history of kind of how this was built up. But what Einstein said is, you know what? If we treat light as a particle instead of a wave, I can explain this. And the way I'm going to explain it is I'm going to say that light consists of photons. Okay, so a photon is a particle. Okay, it's a particle of light. So a photon is a massless particle of light. And if we treat it like that, the energy of one photon, photon is going to be equal to h times the frequency. So here's our frequency again. That'll be in hertz. This is what we were before. Now, what is h? H is Planck's constant. Okay, so where did this come from? There was earlier work done by Max Planck to explain a separate thing called the black body emission spectrum. Okay, so classical physics was kind of really falling down the job at this point, and there was this black body emission spectrum, and he couldn't explain it as well. And so to explain that, he came up with this constant. He said, okay, light can come in these packets, and it was essentially it was this equation, and he came up with this constant of Planck's constant, and this constant is 6.62 times 10 to the negative 34 joules seconds. Okay, so that's what it's an extremely small number. Okay, extremely small number, and fundamentally, for those who are interested, since this is so small, this is why we don't notice quantum effects in our everyday life. Okay, in order to notice these quantum effects, we have to get really small, we have to get really light, and that's not usually where we inhabit. But here's the point, okay, with this equation. So here's another equation. This is in joules, by the way. So this energy of a single photon is equal to Planck's constant times this frequency. So this explains it, because if you're below a certain frequency of light, then you don't have enough energy to eject this electron from the metal to it's the ionization energy essentially is what we're talking about, right? And you don't have enough energy to eject that electron from the metal. Whereas if you're above that frequency, then you do have enough energy, okay? And if the light's really bright, you'll eject more electrons, but they'll all fly off with the same kinetic energy, essentially. So here's another important equation for you guys, to get down in your notes. This E equals h nu, the energy of a single photon, okay? All right, so once again, let's look at this electromagnetic spectrum. Okay, I just want to make sure everyone has this down. So this was shown in terms of high frequency, low wavelength, and then we have wavelength increasing this way. And the energy increases going, so energy increases with increasing frequency. So the energy increases in that direction. And as I mentioned in class, different areas, we use different areas to probe different things in the molecules. So this visible region, this is for electronic transitions. Okay, so this is electronic transitions. So these, this frequency, this wavelength region of light causes electrons to go from ground states up to excited states. Okay, and it's also, kind of what lends things, their color. This IR, this is where we look at the vibration of molecules. Okay, so using infrared radiation, we can cause the molecules to vibrate in different ways, and they will absorb certain frequencies of IR, let others pass through, and by the frequencies that get absorbed, we know how they vibrate. We can say, oh, that's an alcohol, that's a carboxylic acid, that's an aromatic compound. They each have kind of like these fingerprints, right? Microwave, this is where we look at rotational motion. Okay, so this is mainly used in atomic spectroscopy where we're looking at like gaseous atoms. We can use these in MRI is used, and there's also a technique called NMR that also uses radio waves as part of that. Okay, so the difference in energy levels, gets smaller and smaller as we go this way. UV, X-rays, this is usually used to ionize things. Okay. So we use X-rays and UV to ionize things, and gamma rays are used extremely rarely. I can't think of a reason why we use them in chemistry. We don't make nuclear spiders or Spider-Man or the Incredible Hulk or anything like that. So anyway, so that's a little bit of background on light and electromagnetic radiation.